We've seen that when two operators, say A and B, share the same set of eigenfunctions, that those operators commute with one another. Now, one of the implications of this is that both of those operators could be measured simultaneously because they share the same eigenfunctions. So in a sense, when their commutator is evaluated and it equals 0, that tells us that they can be both measured simultaneously. But what does that mean for operators that don't commute? Let's use the position and the momentum operators to illustrate this a little bit. So I'll remind you that the momentum operator is just minus IH bar times the derivative with respect to x. So what I want to do is I basically want to evaluate the commutator of x and p, and I'm going to do this by making these sequential operations of x and p on some arbitrary function f of x. So in essence, this will equal minus IH bar x times df dx when I just put them in this order. Or when I put them in the other order, I'll need to be careful about this, because what it means is that I'll be taking minus IH bar d dx of the product x times f of x. And so now I've got to use the chain rule, and the first term is going to end up giving me d dx of x, which is just 1, so it'll give me minus IH bar times f of x, and then the other term will be x times the derivative of f with respect to x. So this would be the result of reversing those. And you can already see that this and this are not equal to one another. And in fact, if we were to evaluate the commutator for this, I would be taking this minus this, but this term here and this term here are the same, so they'll cancel one another. I'm subtracting this, so I'll end up with a plus IH bar f of x. And another way to write this, just so that we're being more formal, I suppose, is we could write this as IH bar times the identity operator operating on f of x. That way, this commutator of operators gives me an operator back. The effect of the identity operator is simply to multiply by 1. So it doesn't have a huge cosmic sense, but it does allow us to rewrite this as an operator itself. Now what I want to do with this is take a look at what this means for the measurement of different quantities when we want to measure both the position and the momentum at the same time. Now to do this, I'm going to have to organize a little bit of mathematical definition. And in particular, if I have the average value of some quantity, I'll remind you that for a normalized state, this would be written as psi star times the operator A that corresponds to that observable d tau. Okay, so that's going to be that. All right, if I wanted A squared, I would need to have the average value of the operator applied twice in the middle between these two versions of this normalized function. So it turns out that if I look at the quantity A operator minus its average value and square that, I would get the operator squared minus 2 times this average value times the operator plus the average value squared. Okay, well it looks like I'm getting something close to what I need for a variance, but I'll note that when I sandwich this set of things between these normalized states, it turns out this will simplify to simply be equal to A squared minus A quantity squared. And this is something that we identify as the variance squared for this property. I've done this a little bit quickly, but what I wanted to do was basically to demonstrate that this integral is equivalent to this variance. Now, why would I want to do that? Well, there is an interesting mathematical relationship. If I have two different properties, alpha A and B, and I want to measure the product of their square variances, I can show that it's greater than or equal to minus a fourth times the quantity integral this psi star times the commutator of their corresponding operators, d tau. And now I'm going to square this on the outside. So using this property that I've outlined here, I can actually show that this is true. I'm not going to do it here for you. I think you've probably seen enough math for one day. But I will note that when these operators commute with one another, when that is true, then the product of these variances is greater than or equal to 0. So it's basically saying the variances themselves could be as small as 0. We can measure these things very precisely. All right, so why do this? Why would I be interested in this? Well, what I want to do is I want to substitute in the result that we've gotten now for the momentum, position and momentum operator, commutator. All right, so if I use that in here, so if I want to, for example, evaluate psi x psi p squared greater than or equal to minus 1/4, I've got to have x and p in here as the commutator, but I know that's just going to be equal to IH bar. So this is going to end up giving me minus IH bar squared, and then I'm going to have the square of an integral that, since this function is normalized, is a trivial integral to evaluate. It's just going to be equal to 1. This is just equal to 1. So all I have really is the minus IH bar squared. Okay, when I square that quantity here, I'm going to get negative h bar squared. So the negative is going to cancel with the negative out here, and this is going to be equal to h bar squared over 4. All right, so I have this interesting and tidy relationship that the square variances for the position and the momentum are greater than or equal to h bar squared over 4. If I then take the square root of this, I will end up with this relationship, which I hope you will recognize now as being the same as the Heisenberg uncertainty principle relationship that we have seen in earlier videos. So what we've basically shown here is the fact that x and p do not commute leads to, with a little bit of math, the uncertainty relationship that you can't measure them both simultaneously, that the error or the variance in their measurement must be greater than or equal to Planck's constant divided by 2, or the reduced Planck's constant divided by 2. So this leads us to a series of equivalent statements, and I want to really outline these because I think it's really instructive that these statements are all equivalent to one another. Okay, the first statement is that the commutator of x and p is equal to IH bar times the identity operator. All right, so they do not commute. Since they do not commute, x and p do not share eigenfunctions. Since they do not share eigenfunctions, x and p cannot be measured simultaneously. I should say with precision. They could certainly be measured simultaneously, but you would have a great variance in them. And the final part of this is that with all of these things being true, the product of the variance of these two is always going to be greater than or equal to h bar over 2, the uncertainty principle. So, in other words, these are all equivalent ways of basically saying the same thing. So if these things don't commute, I've got the uncertainty principle. But it also means they do not share eigenfunctions. It means that they cannot be measured simultaneously. So you'll hear all of these things stated, but mathematically they're all connected to one another, and they all must be true if one of them is true.